Brem's X-ray creation involves just the losing of kinetic energy of the projectile electron. So the electron gets close enough to the nucleus of the atom that that gravitational pull of the nucleus causes a change in direction of that electron, and as it changes direction, it loses some of its kinetic energy. The closer it gets to the nucleus of the atom, the more energy it's going to lose. The energy level of the Brem's X-ray creation is dependent on that loss of energy. So again, if we have a big nucleus, then we've got a great gravitational pull and a very large target for that Brem's or that electron to get close to. So the more energy it loses based on the size of that nucleus and the proximity with which it gets to or close to that nucleus, the more energy it's going to lose and the higher the energy of that X-ray that gets created. But remember that most of the atom is empty space, so most of the electrons don't get close to the nucleus, and so they lose less energy than what you would hope that they would. The result is that most of the X-rays that are created as Brems, but most of the X-rays are going to be low energy photons. So again, we go back to the visualization of the Brem spectrum as it comes off of the target, and most of the X-rays that we create are low energy photons with very few high energy X-ray photons. Can we influence the likelihood that we're going to have higher energy X-ray photons created? Well, yeah, we can. Part of that is through the size of the nucleus, so we could change the target atom, but keep in mind the characteristics we need to demonstrate. If we changed from tungsten to gold, yeah, we could certainly increase the likelihood of getting closer to the nucleus of the atom, but the problem is that we would have a target atom that had a low melting point. Our X-ray tube life would be very, very much shortened. But the other thing is that the higher the KVP that we set, the more interactions it might undergo, and the more likely we would be to have a higher energy X-ray photon created. Even still, though, most of your Brem's photons are going to be very, very low energy photons that are going to be filtered out. Most of what we create is Brem's. Most of those Brems that we create are going to be low energy Brems, and we're going to filter out a tremendous number of those. So if it gets close to the nucleus, it loses energy, it slows down, and what happens is we get a conversion of that kinetic energy into electromagnetic energy equivalent to how much energy that electron lost. So if it lost 99% of its energy and it came in with 100 kVps or keV worth of kinetic energy, then we would create a 99 kVp X-ray photon. So how you calculate is the difference between the incoming energy and the outgoing energy of the electron. If it comes in with 100 kVp and it leaves with 1 kVp worth of energy, then the X-ray photon that you create is going to be 99. So the energy level of the Brems can be anywhere from the minimum energy that is emitted from the tube all the way up to whatever it is that you have set. Again, on your Brem spectrum, characteristic is represented as a single spike, and everything else is Brems. 85% of your X-rays created are going to be Brem's X-rays. 15% would be your characteristic. Chapters 7 and 8 are the X-ray beam and things that control creation, control emission, control quantity and quality, and some obviously controlling both. So this is chapter 7 and 8 are a good intro into chapter 13 in our radiographic technique. So things that control creation, you got tube potential in your KVP, you got tube current, and that is your overall mass. You've got generator type, you've got target material. So those are all control X-ray creation if nothing else changes. If you change tube potential, then creation, you create more X-ray photons. If you increase mass, you increase X-ray creation. If you change from single phase to three phase, you increase the numbers that you create. And if you change target material, then you're going to change the imaging characteristics of that X-ray beam. And most of the time, whenever we're changing target material, we're changing from tungsten to something of a lower atomic number. So we actually lose numbers in that conversion. So we've got a difference between creation and emission. So X-ray creation, again, is at the target. So the things that control creation, again, would be your KVP, your MA, your time, target material. Emission, on the other hand, is emission from the X-ray tube. So everything that the X-ray passes through before it interacts with the patient is going to absorb some X-rays. So by the time the X-ray beam gets through the collimator housing, it's going to be greatly different than what it was at the target itself. So the glass is going to absorb some X-rays. Oil will absorb some X-rays. The port in the protective housing will absorb some X-rays. The multi-leaf collimators will absorb some X-rays. The mirror will absorb some X-rays. So by the time it gets to the patient, it's highly filtered. And that's where we draw that on the emission spectrum. Notice it's called the emission spectrum, the emission from the X-ray tube. So KVP, mass, filtration, machine phase are primarily the factors that are going to affect X-ray emission. They affect the numbers of photons emitted. They affect the peak energies in KVP. They affect the average energies, the KVP and the filtration and generator type all affect average. It affects the minimum energy only in the filtration. It affects whether or not we have a characteristic spectrum. If the KVP is not above 69 KVP, then we don't see any characteristic spectrum. The numbers, though, are affected by pretty much everything. KVP, mass, filtration, machine phase. So we call the characteristic spectrum the discrete spectrum because it exists at one energy level. I use some of these terms interchangeably, not just here, but in KVP versus potential energy versus electric potential. I use those interchangeably in a lot of cases because when you get to the registry, it may use the different terms for different applications, and you need to understand that they mean the same thing. So characteristic photons can be created in a lot of different places, but again, the only ones that we're interested in are going to be those inner shell electrons that are replaced by non-bound electrons, and so we get the 69 KVP X-ray photon. The brims, we call it a continuous spectrum because it's non-discrete. It's more like an analog. Every energy level is represented. It's unbroken from one energy level all the way down to the next, from minimum to maximum. They're all there. So MA and mass, what it controls is the heating of the filament. So it controls the filament current. So again, back to chapter 4 and the laws of electrostatics and electricity, where we walk through electricity and the effects of electric current. If you send electrons through a circuit, then you create heat. You create magnetism, but you also create heat. So MA controls the heating of the filament. Thermionic emissions is what we're trying to get to. Thermionic emissions means hot ions, hot charged particles. hot electrons. So an amp is just a unit of electric current. It's a measure of electrons that are flowing through a circuit, and 1 amp is equivalent to 1 coulomb per second. This doesn't really mean anything to you, but a coulomb is that many electrons, so it's a ridiculous number of electrons. So when we make an exposure, we don't really have mass until the exposure actually takes place. So we have MA, that's milliamperage, flowing through, or really it's amperage, but it's amperage flowing through the filament just to heat it up is all we have. We often call it intensity. We also often call it exposure. And the reason we call it exposure, intensity is just numbers, but the reason we call it exposure is because it directly controls the exposure to the image receptor. If you double your mass, you directly change the exposure to the image receptor at any kVp by a factor of 2. So you double your mass, you double your image receptor exposure, you double your patient exposure. So it's an actual measure of the amount of exposure that you're going to give to the patient or to the image receptor. It's a controlling factor of quantity. It is your intensity, it's your exposure. The only thing that it controls is the numbers, and it directly controls those numbers. So what does it control in the brim spectrum? Just that height. That's it. kVp, though, controls a lot of different stuff. kVp, once we apply the kVp, we change the relative positive charge of the anode and the relative negative charge of the cathode so that the electrons travel across the tube. Now we truly have tube current. Until we apply kVp and it goes across the electrons travel across the tube, then all we have at that point is filament current. So now we've got tube current. So kVp controls that electric potential, the relative positive and negative charge, so that it can actually travel across the tube. Before we apply the kVp, the electrons can't make that jump. So it causes the electrons to accelerate from cathode to anode. It changes our current from just a filament current to actually tube current. It controls the electron speed, so the higher the kVp we apply, the faster those electrons travel across the tube. Now remember, once they become X-ray photons, they all travel at the same speed, and the difference in energy level is only the frequency and wavelength. So they travel all at the same speed, that being speed of light. So changes in, when we change kVp, we get an exponential change in the number of photons that we create. Remember, whenever you increase your kVp by 15%, if you want to maintain the same exposure to the patient, then you have to change your mass accordingly. So if you increase your kVp by 15% and you do nothing else, then your exposure changes by 100%. If you want to maintain your exposure, you have to reduce your mass by a factor of 2. So it controls the maximum energy of the photons created, and it's really the only thing that controls that. It determines whether or not we've got a characteristic spectrum, and it determines the energy level of the X-ray beam. So it changes the average. It pushes the average towards the high energy side in the brim spectrum. The very peak of that bubble goes towards the high energy side. And it is the reason that we don't use it as the primary control of numbers, is because it changes the imaging characteristics of the X-ray beam. Whereas mass only changes the numbers, kVp controls or changes everything. So what happens in the X-ray tube, again, is the potential difference between cathode and anode changes. That changes the kinetic energy of the electrons. But in the beam itself, and the beam as it interacts with the patient, it controls a lot of stuff. The penetrability, since it controls the penetration of the X-ray beam, it can control the absorption characteristics. It will control the absorption characteristics, which can have, as we'll learn, effects on the image itself. Now, full disclosure, the image itself is really mainly controlled, and the appearance of the image is mainly controlled not by KVP, but rather by the computer algorithm that we apply to a particular image. And what I mean by that is, on a chest X-ray, traditionally we use high KVP to penetrate the ribs and the mediastinum. And our computer algorithm that we apply to a chest X-ray is intended to give us a wide shade or wide scale of grays that would be representative of the chest X-ray. A computer algorithm for ribs, on the other hand, is supposed to give us a higher contrast so that we can see the ribs much better than we would on a chest X-ray. If we use the same technique on a chest X-ray as what we used on a ribs, but we applied the rib algorithm to that image, it would look like a set of ribs. But if we use the same thing and we applied a chest algorithm to it, the machine would make it look like a chest X-ray. So KVP really doesn't control the contrast nearly as much as what it used to. It can influence it though. So the absorption characteristics and the penetrability of the X-ray beam can still affect the image. So it dramatically affects X-ray production as KVP goes up. If nothing else changes, then the number of X-rays we create goes up, and it even becomes more dramatic in the emission itself. So what does it do? On the brim spectrum, it changes the height because it does affect quantity, and this is assuming that we've got an increase in KVP. It increases the peak, it increases the average, and it determines whether or not we've got a characteristic spectrum. So it controls everything except for the minimum. So again, the minimum has everything to do with filtration. Our average is here as opposed to here, so it moved it towards the high energy side. We already had a characteristic spectrum, so it probably changed how many characteristic photons we actually have. But we get an increase in numbers, we get an increase in average, we get an increase in peak energy, and then again, if we had not had a characteristic spectrum, we would have one now. So the behavior of photons, they're similar to light. They have some differences, but they have some similarities as well. So how they differ in energy level between light and different types of electromagnetic energy is just a frequency and wavelength.